All right, so in this lesson, we combined together the 3 different measurements we can make with respect to electromagnetic radiation: wavelength, frequency, and energy. Okay? So the first formula that we looked at was the following. We said C equals lambda, which is your wavelength, times nu. Keep in mind your speed of light here is going to be 3.00 times 10 to the 8th. Okay? Its units are meters per second, which helps highlight the fact that your units for your wavelength need to be in meters, and your units for frequency will be in either seconds to the -1 or hertz. The other formula that we looked at was this energy formula. E, energy, which is in joules, equals Planck's constant times your frequency. And your Planck's constant here is 6.626 times 10 to the -34th. And its units are joules times seconds. Okay, so I will interchangeably be using these formulas to solve problems, so let's actually look at some examples. So for the first one, it says, what is the frequency of photons with an energy of 1.4 times 10 to the -21st joules? So I'm going to be using my energy formula. Energy equals Planck's constant times my frequency. My energy here is 1.4 times 10 to the -21st. That equals my Planck's constant, which is 6.626 times 10 to the -34th. And I am solving for my frequency, so I'm multiplying by frequency. So I'm going to divide both sides by my Planck's constant, 6.626 times 10 to the -34th. Keep in mind when you actually do this in your calculator, be careful. Make sure that you put Planck's constant, the 6.626 times 10 to the -34th, make sure that you put it in parentheses in your calculator. So the value that I get for frequency unrounded here is going to be 2.113 times 10 to the 12th. Keep in mind I've got to figure out my sig figs here. So 1.4 has 2 sig figs, 6.626 has 4, so I want my final answer to have just 2 sig figs, so 1, 2. So this will actually just round to 2.1 times 10 to the 12th. Keep in mind my units here need to be in either hertz or seconds to the -1, so I'm just going to put hertz. Okay, let's look at the next practice problem. All right, for the next practice problem, ultraviolet radiation has a frequency of 6.8 times 10 to the 12th kilohertz. Calculate the energy. So the only issue with this problem is the fact that I'm right now in kilohertz, but I need to be in hertz in order to use my energy formula. So I'm going to quickly convert that. If I'm in kilohertz right here, I can easily get out of kilohertz by putting it on bottom and put hertz on top. I know that 1 kilohertz is 10 to the 3rd hertz. And so what I'll get when I multiply 6.8 times 10 to the 12th by 10 to the 3rd is I will get 6.8 times 10 to the 15th, and I'm now in hertz. So now I can use my energy equals Planck's constant times my frequency formula. I know Planck's constant is 6.626 times 10 to the -34th. I know my frequency now in hertz is 6.8 times 10 to the 15th. And so what I end up getting for my energy is unrounded 4.5, let's say 1 times 10, and this is going to be to the -18th. Now keep in mind if I look at significant figures, 6.8 has 2 sig figs, so my final answer here I want just to have 2 sig figs. So this is going to be 4.5 times 10 to the -18th, and my units here are going to be joules, because those are my units for energy. Let's look at the last practice problem. It says, what is the energy of light that has 434 nanometers? So that's the wavelength. So here's the problem. In order to calculate energy, I'm going to show you my 2 formulas here right now. In order to calculate energy, I need to know my frequency, and I don't know my frequency right now. I know my wavelength. The other problem I have is right now I'm in nanometers, but I need to be in meters in order to use this equation. So this is going to be a multi-step problem. I'm going to start out by noting that I need to convert 434 nanometers. I need to get that out of nanometers, and I need to first get that into meters. So I'm going to put nanometers on bottom, and I'm going to put meters up top. So 1 nanometer is 10 to the negative 9th meters. And so what that'll give me when I multiply by 10 to the negative 9th, this will be 4.34 times 10 to the negative 7th. Okay, and that's in meters. So now when I'm solving this, I'm going to use my speed of light equals wavelength times frequency formula. My speed of light is 3.00 times 10 to the 8th. I know my wavelength here. It is 4.34 times 10 to the negative 7th times my frequency, which is what I'm solving for. So I'm going to divide both sides by my 4.34 times 10 to the negative 7th. Okay. Remember, when you put in your calculator, make sure to put this in parentheses. Okay, and so what I get when I solve for my frequency is 6.912, and I'm going to keep this in my calculator because I'm going to use this in just a second, but I'm going to put a slightly rounded value down on my paper, times 10 to the 14th. And remember, your units for frequency are either hertz or seconds to the negative 1. However, it's not asking for my frequency, it is asking for my energy. So I need to go one step further, and remember your energy equals Planck's constant, which is 6.626, times 10 to the negative 34th, and I'm going to multiply that by my frequency, which I got here to be, this is the rounded value. I'm going to use the unrounded value when I'm actually using my calculator, but there's my frequency there. So I'm going to take the 6.912, etc., that's in my calculator, multiply that by 6.626 times 10 to the negative 34th, and what I get for my energy unrounded right now is 4.580, let's say, times 10 to the negative 19th. Keep in mind, if you look here, 434 has 3 significant figures, so 1, 2, 3. So my final answer here will be 4.58 times 10 to the negative 19th, and my units are going to be in joules. Now notice for the problem, it didn't ask or didn't specify what units you needed to be in, so you can stay in joules if you want to, that's totally fine. Or you could even convert to kilojoules if you want. If I don't know what units you need to be in, you can choose the units you want.